All right, we're going to switch gears a little bit for this video. We're going to do a different kind of a study in a way, and let me set this up. Suppose that we wanted to study whether or not there's a relationship between alcohol use in students and their grades, their academic performance. Okay, and so what we might do is a survey where we ask them to indicate how much alcohol they drink, okay? And then we're going to ask about their GPA, okay? Now, this again is a little bit more complicated than you might think at first blush because we have to think about the methodological issues related to survey research. So firstly, of course, I would probably want to do this survey anonymously because of the nature of alcohol use and being of age and all that stuff. We would want people to feel free to respond honestly. Of course, even if you do the survey anonymously, it doesn't guarantee that people are going to be honest, but we can ask them. And then also, when we talk about alcohol intake, there are some issues related to that variable, and we can go way back to the beginning of the course and talk about, operational definitions. What do we mean by alcohol intake? And if I ask people to indicate how many drinks they have, let's say per day or per week, we have to be a little bit careful about that question because, if you have a big mug of whiskey sours, that's going to be different than some kind of seltzer, alcohol seltzer, and that's going to be different than beer and whiskey or whatever. So we need to somehow make it so different drinks are sort of made equivalent, right? And oftentimes people talk about ounces of alcohol, and maybe what we'll do is we'll say, have people indicate how many ounces of alcohol per week. So, and as a general rule, kind of like 1 can of beer has 1 ounce of alcohol, so does 1 ounce of spirits, and then maybe a 10-ounce glass or 8-ounce glass of wine. Okay, so we're going to equate those in terms of their alcohol content. So we'll say, how many ounces per week do you ingest? And then we're going to ask about GPA. And of course, we have to be careful about GPA because you could do semester GPA, you could do cumulative GPA, you could do GPA within your major. So let's talk about the GPA for the semester that we're asking them to indicate their alcohol use. Okay? Again, we could spend an entire semester really talking about the issues related to survey research and how you do survey research well. For our purposes, we'll talk about the data, right, and how to analyze the data once we have done the research and have the numbers, okay? So the one thing we're going to want to acknowledge, though, is we're going to get, so if this is student number 1, we're going to get 2 measures for that student, right? We're going to get their alcohol intake. Let's say it's 40 ounces per week, and that is 40 ounces of alcohol. So this is 40 cans of beer a week, and maybe their GPA is 0.8. Oops. That's not too good, right? Probably going to get kicked out of school for that one. And then subject number 2, let's say, has 4 ounces per week, and their GPA is 3.4. All right, I'm just making these data up, folks. Subject 3, then, let's say, 1 ounce of alcohol per week, and they have a GPA of 3.2. Okay, and we can keep going. Let's do 9 subjects, okay? a very, very small survey. In fact, it would be too small to even present at a conference, but it's small so that we can deal with these numbers and do things by hand. And then again, I will show you how to do this via a computer program, and where we can analyze perhaps 500 or 237 or 612 subjects, that we survey. So let's just put these numbers up here. And number 6 is 30. And let's do this. And for 7, it's 21. And okay, for 8. So here are our data, okay? Now, here is the big difference, and please listen carefully, okay? And I'll try to explain to you that the question is different now, right? Before, when we did our z-scores or our t-tests or even our analysis of variance, we were looking to see whether there was a difference between two groups, or a difference between a single group and some mean, or a difference between 4 different groups, right? We were looking at average differences between the groups. In this case, I'm not assessing whether there's a difference between the average amount of alcohol you drink and the average GPA. That would actually be kind of a silly question, right? Listen carefully. I'm not asking whether there's a difference between the average alcohol intake and the average GPA. That's not what I want to know. I want to know whether there's a relationship between the two variables, okay? Whether there's some kind of an associative relationship. That's a difference in the question that I'm asking. That's a difference in the question I'm asking. I'm not asking whether there's a difference between the two groups. I'm asking whether there's a relationship between the two groups. And what do I mean by that? Well, as one variable changes, do we tend to see associated changes in the other variable? Right? That's the question. Could we do a t-test with these two groups of numbers? Absolutely. I hope that you could do a t-test here. But it wouldn't make much sense because I'm not looking to see if there's a difference. I'm looking to see whether there's a relationship, whether changes here are associated with changes here. Okay? So it's a difference in the question that we're asking. And I can tell you one thing, when I was in graduate school, I got a lot of free beer for helping people with statistics. That's one of the benefits of knowing your stats. I made lots of friends and I got lots of free beer because people would come in and ask me for help. And they would come with a data set like this and they might remember T for 2, right? T for 2. I have 2 groups, so can I do a t-test? Well, a t-test is used to assess whether there's a difference between the 2 groups. That's not what we want to know for this research, okay? I want to know, do people who drink more alcohol, are they showing higher GPAs? Are they showing lower GPAs? Or is there no relationship, okay? So it's a relational question that I'm asking here, okay? And in fact, I have 2 variables for each subject, right? My X variable and my Y variable, 2 variables. I'm looking at a relationship between 2 variables, okay? Now let me ask you this question. If you have 2 captains on a sports team, what are they referred to as? Right? The co-captains. If I have 2 or 3 or 4 authors on a research article, what are they referred to as? They're co-authors, right? So here we're doing a co-relationship, okay, or correlation, okay? I mean, that's kind of, maybe that's the source of this word. Instead of a hyphen, we put in an extra R, right? A co-relationship, a correlation, a correlation, because we have these two variables. And what I would like you to do when you're faced with an analysis like this initially is let's create a graph. We're going to create a scatter plot, or sometimes people call it a scattergram, of these two variables. And we'll sort of take a look at how the points look in this distribution. Before I do that, let's take a look at the numbers. What do you think? What do you think? Do you think there's a relationship between the alcohol intake and the GPA for students? How would you describe the relationship that you think you're seeing here? Right? Well, the students that are drinking more alcohol generally are showing what? Lower GPA. And the students that are drinking less alcohol looks like they are they have a higher GPA. Now, I hope by looking at these numbers you can sort of see that, right? And that's the question that we're asking. That's the analysis that we want to do. Is there a relationship? Okay. But let's do our scatter plot, and we might be able to see it visually a little bit better. Now, if this was a real survey and we had 500 respondents, you wouldn't be able to sort of look at it and just eyeball the data. You would need to do the analysis, and initially you would need to do a scatter plot to sort of see the relationship, I think. So here's what we're going to do. Okay, we are going to make a graph with an x-axis and a y-axis. Our x variable is alcohol intake, and make sure you label your axes. Just because you have numbers doesn't mean that's a label, okay? This is ounces per week, okay? And we have to go up to 40, so let's do this. 10, 20, 30, 40, okay? And these are the fives, right? Do something like that. For our y variable, let's put GPA here, okay? And of course, we need to go up to, let's go up to 4. That's the highest you can get, right? 4.0. Now we can place our data in this two-dimensional space. So each subject is giving us Cartesian coordinates, and hopefully that made some neurons, fire in your brain from high school. This is a Cartesian coordinate. So subject number 1, 40 ounces of alcohol a week, and their GPA is 0.8. Okay. Subject 2, 4 ounces of alcohol per week, and their GPA is 3.4. Okay, so each person is represented by 1 point on the graph. It's their Cartesian coordinates. Here's subject 3, 1 ounce of alcohol, and they're at 3.2. Okay, 27 ounces of alcohol, and they're at 2.7. Something like that, maybe a little higher. I mean, if you're doing this on a computer, it would make it nice and accurate. 16 and 3.0, okay, 30 and 2.0, 21 and 3.2, oops, something like that, okay, 10 and 3.5, and 12 and 2.9, okay. And so we can see from this graph that there is a general trend, right? There's a general trend here that people who are higher on alcohol intake end up getting lower GPA. People that are lower in alcohol intake are higher GPA. So it looks like something like this. As we see X going up, we see Y going down. Or as we see Y going down, we see X going down, we see Y going up. The variables are changing, right, in opposite directions, okay? And that's why we see a pattern like this, higher on the X, lower on the Y, lower on the X, higher on the Y, okay? And in fact, this is called a negative correlation. This pattern of relationship is called a negative correlation. That doesn't mean, listen carefully, that doesn't mean that there's not a relationship, right? When I say a negative correlation, where the word negative comes from is because this has a negative slope, okay? When we look at a pattern, it generally has a negative slope. If we had two variables that created a graph with a slope like this, where the higher your X, the higher your Y, right? So if we had something like this, where the variables are changing in the same direction, either both going up or both going down, we call this a positive correlation, okay? And that's because if you plotted this on a graph, it would give you a positive slope, okay? So the word positive and negative has to do with the pattern here, the slope of the line. It doesn't have to do with whether you're positive there's a relationship or negative there's a relationship. That's not the appropriate way, okay? So in this case, then, we have the pattern of relationship is a negative correlation, okay? Now, what we're going to do is we're going to do a statistical analysis of this relationship and see if it's statistically significant. Just like we've done before, when we look at differences, we say, is this a statistically significant difference? In this case, we're not looking at differences, but we're going to say, is this a significant relation? Is this a significant correlation between these two variables? Okay? So we will get back to this in a little bit once we do our statistical analysis. Okay? So let's get rid of this for now, and I'll show you how to do this statistical analysis. And here's what we're going to do. We're going to use something called, and believe me, relative to the analysis of variance, this is going to be quite straightforward for us to do. Because here's the analysis we're going to do. We're going to do something called Pearson's R. That's the letter that we're going to use for this analysis, right? We've had our z-scores, our t-test, we've had Q, we've had Hartley's F max, we've had analysis of variance with an F, and all that stuff. Well, this is a Pearson's R value, so it's going to tell us about correlation. And here is the formula, okay? The formula is this. In the denominator, we're going to do this. We're going to look at sum of squares for x. So here's the x column. Let's do our sum of squares, okay? Can you do that? You better be able to do that because we've been doing it for a long time, right? And then sum of squares now for the y variable. And so we're going to do the sum of squares here. And these are multiplied together. Okay? These are multiplied together. We're going to take the square root. That will be the number that we have in our denominator. Okay? In the numerator, we have something a little bit different, and it is called SP. And that is the sum of products. Okay? This is sum of squares, right? This is sum of squares for x. This is sum of squares for y. This is called the sum of products. And let me show you, let's do this. Okay, I can put this up here, sum of products. Okay, that's a y. So, sum of products. Let me show you sum of squares formula. Okay, here's the sum of squares formula, and you don't have to memorize it, but we've used it so often you probably almost have it memorized, right, just from use. So there's the sum of squares. We'll use that to get our sum of squares for x. We'll use that to get our sum of squares for y. Okay, even though it's x's, I mean, it's just saying use these numbers when you get the sum of squares for y. Use these numbers with sum of squares for x. But I just want to show you, because it's kind of cool, I think. You don't have to derive this, but I just want to show you. I'm going to expand this a little bit, because really sum of squares is this. We're going to take the sum of x times x, right? Because that's x squared. The sum of, in this case, would be 40 times 40, right? Plus 4 times 4, plus 1 times 1. I mean, that's what the square tells you, right? And then I'm going to expand this out. Okay? I just want everybody to see. I want everybody to see that this and this is the same formula, right? This shorthand notation of square, I just wrote out long fashion, right? X squared is x times x. Okay. Well, here's what we're going to do to get the sum of products. It's actually very similar to sum of squares, but here we go. We're going to replace one of the x's with a y. We're going to replace one of the x's with the corresponding y, okay? And so this then becomes the sum of products, okay? Sum of squares, sum of the products of these two things, okay? So something a little bit new, but not as new as you might think, okay? So we're going to get rid of this. We'll use this for our sum of squares. This is our sum of products. In order to get the sum of products, I mean, let's look here. Can we get the sum of x's? Yeah, that's pretty straightforward, okay? Can we get the sum of the y's? Yeah, that's pretty straightforward, okay? The n here is a little bit funky. The n is going to be the number of pairs that we have, which is 9. Or, the way I like to think about it, it's the number of points in that graph that we made. So this n here, this n here is 9. This n here is 9, okay? That's the one place that I think is the most confusing. And before we do the computations here, I'm assuming that you can do this computation, okay? I hope that you can do that. You better be able to do it, right? But before we do this computation for the sum of products, I need to get this value. And what is this saying? It's for each person, I'm going to take their x value and multiply by y. For each person. then I'm going to add that up. So we'll do that 9 times. So when you get ready to do your Pearson's R computations, it's best if we make another column here, and that is the X times Y column. Okay? So I want to do 40 times 0.8. Now before you take your calculator out, look at my hand, yikes. Before you take your calculator out, 40 times 0.8, and people are like, oh, I don't know what that is, I don't know what that is. I said, listen, I told you at the beginning of the semester I'm going to help you with your math, right? Hopefully you've gotten better. I think you have. So listen, there's only 2 numerals here. There's only 2 numerals here. There's a 4 and there's an 8. Okay? So what's 4 times 8? 4 times 8 is 32, right? But I want 40 times 0.8. So, oh my gosh, I don't know what to do. I don't know what to do. Well, just settle down, right? If my numerals are 4 and 8, I know the answer is going to be 3.2, 32, 320, 0.32, 3,200, okay? Because, I mean, the numerals are 4 and 8. Okay, so this is what's going to be the multiplication. I just need to figure out where to put the decimal, right? Well, listen, what would be 0.5 times 40? Half of 40 is 20, right? So this is 0.8 times 40. It's not good, 1 times 40 is 40. 0.5 times 40 is 20. I know the answer is going to be somewhere between 20 and 40. So of these possibilities, what's between 20 and 40? Bingo, 32. Now, use your calculator, folks. I always want you to use your calculator. I use a calculator all the time. But just because I use a calculator doesn't mean I'm going to put my brain in the closet. Okay? So use your calculator to verify your thinking, right? So this is 32, and this is going to be 12 plus something, right? Let's do it. 3.4 times 4 equals 4 times 3.4 equals 3.4 times 4 equals 13.6, okay? And this is 3.2, okay? And this is 27 times 2.7. That's 72.9, okay? And 16 times 3 is 48. And 30 times 2 is 60, okay? And 21 times 3.2 is 67.2, and 35, and 12 times 2.9 equals 34.8, okay? We're going to add all these together. That's the first part of my equation here, okay? Let me just make sure I did this correctly. 40 times 0.8. Yes. 3.4 times 4. Yes. Okay. I got that one. 27 times 2.7 equals 72.9. 16 times 3 equals 48. 60. I mean, I don't want to make a mistake, right? 67, 35, 12 times 2.9 equals 34.8. Okay, so I'm going to add these up. And what do I get? 32 plus 13.6 plus 3.2 plus 72.9 plus 48 plus 60 plus 67.2 plus 35 plus 34.8 equals 366.70. Okay. Of course, I'm going to do it again. Plus 34.8. Okay. Now this one, let's add these numbers together. So 44 plus 28 plus 46 plus 31 plus 12. That's 161. And then 0.8 plus 3.4 plus 3.2 plus 7 plus 3 plus 2 plus 3.2 plus 3.5 plus 2.9. 24.7. Okay. Just going to add up the y's, add up the x's. Those are going to be multiplied together. I'm going to quick double check here. $161. Yep. Okay. 0.8 plus 3.4. 24.7. Okay. So now we have 161 times 24.7 equals, divided by 9 equals. So we have 366.70 minus 441.86. Okay? 366.7 minus 441.86 equals negative. So our R value here is negative 75.16. That's our sum of products. Okay? Now we're going to do the sum of squares for x and the sum of squares for y. Multiply those together and then take the square root. Okay? So I'm going to have you pause the video and you can get the sum of squares for x, sum of squares for y. So we're just going to take these numbers and get the sum of squares, right? Take these numbers and get the sum of squares. Plug that in to the formula. Multiply those two together. Don't forget to take the square root. Don't forget to take the square root, okay? And if you do that, what you will find, well, I thought I had my numbers here. Let me have you pause and do that. We'll get to our R value. One thing before you do that, though, I just want to point out, when you do the sum of squares formula, you will never get a negative number. When you do the sum of squares, you'll never get a negative number. The reason for that is because you're squaring, right? We talked about this a long time ago. You're squaring each of the values. But conceptually, you will never get a negative number because sum of squares represents variability, right? And so there's either some variability or there's zero variability. If all the numbers are the same, it's zero variability, right? So both conceptually and computationally, you'll never get a negative number with sum of squares. If you do, you made a mistake, okay? However, for sum of products, you can get a negative number. And in fact, if you have a negative correlation, right? If the variables look like they're moving in opposite directions, okay? If they're moving in opposite directions, like what we see in this data set, then that's where that will be reflected in the sum of products. If you had a positive correlation where both variables are changing in the same direction, can we think of an example? Let's suppose we looked at the temperature in a baseball stadium and the amount of beer that's sold. That would probably be a positive correlation, right? The higher the temperature, the more beer sales. Okay? Or the lower the temperature, the less beer sales. That would be positive. In that case, your sum of products would be positive. Right? If you have a positive relationship, the sign of the sum of products tells us what type of relationship we have. That is either positive or negative. Okay? So I'm going to have you pause the video and you can do the sum of squares. Actually, we'll start a new video once you do that, and we'll see if you come up with the same numbers as I do.